DynamoDB scaling is really divided into two dimensions here. One is throughput. That's our read and write capacity. And then we also have size. Now, any single item can only be 400K, but we can store as many of those 400K items as we want to. There's basically a limitless amount of space that AWS gives us. So if we recall back to our lesson on DynamoDB, we have this concept of a partition. That's a physical space where DynamoDB stores the data, and these are divided up into 10 gigabyte chunks. We also have the partition key, and that's that unique identifier. It's also sometimes called a hash key, and you'll see why later. Then we have the sort key, and in combination with the partition key, you can create a composite key that defines how that record gets stored and how it can be retrieved. And sometimes this is called a range key. Now, under the covers, Dynamo scales out by adding partitions. And here's the formula for how we decide how many partitions we get. So there's two dimensions. One's by capacity, and the other is by size. So by capacity is how many read units and write units we've provisioned. And then for size, it's how many 10 gigabyte chunks we take up. And so our total partitions are going to be decided by the maximum of either the capacity calculation or the size calculation. Let's look at an example. So in this case, I have a 10 gigabyte table. I have 2,000 read capacity units and 2,000 write capacity units. So my partition calculation by capacity would be 2.66. By size, it's 1. And so my total partitions are going to be the max of either of those, which is 2.66. But because I can't have a fractional partition, I get rounded up. So I'm going to have 3 partitions. So in this case, note that the read and write capacity has been equally allocated across our partitions. Now, AWS does allow some burst capacity. It allows me to exceed some of that read and write capacity against a single partition if I'm not using that in those other partitions. But really, we should design our partition keys around trying to avoid this whenever possible. And I'll show you the problem that we'll run into. So let's look at how DynamoDB actually decides how to land hashes on the different partitions. Now, as you remember, when we talk about the partition key, it doesn't get stored as the text value that you pass in. It gets translated into a hash value. So if we have one partition, all the data is going to land on that same partition. So there's really not much we can do from a spreading the load around standpoint. Now, if we increase our read capacity or write capacity, or we reach that 10 gigabyte cutover, now we have maybe 2 partitions. And in essence, DynamoDB just divides the data down the middle and says 50% is going to go to partition 1, 50% is going to go to partition 2. And it's based on the hash value or the partition key hash. And if we go to 3 partitions, it's going to do the same thing. It's going to divide them into 3s. So you can see why it's beneficial to have a partition key that has a degree of variability in it for the data, because that's going to help us equally spread the load across the different partitions. Let's take, for example, a scenario where we've designed a data collection system where we're getting data from sensors, and we've chosen to use a partition key of date. Well, the problem is we get a lot of sensor readings every day. So from a write perspective, we're going to be hitting that same partition, because when the date gets hashed out, it's going to be the same. So we're probably going to be consuming all of our write capacity against that one partition pretty quickly, whereas partition 2 and 3 go unused. Similarly, when we go to read it, we're going to be slamming a single partition and not distributing that load across all the partitions. This is known as a hot partition or a hotkey issue. Now, alternatively, what we could do is choose to make sensor ID as the partition key, and then use date as the sort key. Now, when those sensor IDs get hashed out, chances are they're going to be landing on different partitions. And so this makes better use of our write capacity. Additionally, it makes better use of our read capacity because we're going to be able to spread that read load across many partitions. Now, DynamoDB also has the ability for us to specify auto scaling. And when we reach a certain target utilization, we can scale up our provision capacity for read or write units. In essence, it looks like this. We're going to specify a certain provisioned limit. And once we reach that limit, the DynamoDB configuration is going to trigger a CloudWatch notification, which is going to tell our application auto scaling process to go update the provision capacity on that DynamoDB table. And we could also have an SNS notification go to us and let us know that that's happening. Now, there are some things to note about auto scaling for DynamoDB. It uses this target tracking method to try to stay as close to possible as that target utilization. And right now, there's really no good way to scale down if that table's consumption drops to 0. And that's because DynamoDB doesn't know if it's just simply not being used or truly the demand is gone for good. Workaround number 1 is we can just send requests into the table until it auto scales down. So we could keep requests going at a very minimal level. And then DynamoDB will finally figure out, okay, the average load has dropped, so I'm going to scale down. Workaround number 2 is that we can manually reduce the max capacity to be the same as the minimum capacity. So in essence, what we're just saying is scale down to some minimum capacity that we had before you decided to scale up. Now, autoscaling also supports global secondary indexes. And this makes sense because you got to kind of think of global secondary indexes as just a copy of the original table, just indexed or keyed differently.